Yeah. So the random color chosen by the system is basically happens to be light coral. There can be so many colors. Okay, it is right there. Once I press G for gray over there and send it to the serial monitor, see the color is gray and it will stay for 5 seconds. After that, again, 2 seconds, it will come back to another, color, random color, which is aqua cyan. Again, let's say I'm selecting O for olive. The olive stays for 2 seconds. Again, it will actually it goes back to another random color, for example, orange. Now you have, it's a T for teal. Goes to honeydew. Next, M for maroon. Goes to yellow. Last we have, I think, what are the words actually? I forgot. Okay, P for purple. And it goes to again light coral, whatever actually. So you can choose your own color also. But the catch is that again what I think solution we had discussed, that it will not stop simulating one thing. Okay, it will keep on doing certain things parallelly. Once it gets triggered with an input, with a keyboard interrupt or stuff like that, it will accept that input based on the priority. It will perform the task. Again, it will come back to the previous one, right? Kind of.
And when it changes to another color, it stays in that color one. Again, it will not shift to another one, right?
It doesn't stays with that color because I'm using random command. This is random. Okay, had it been, but if it's quite determined, okay, fine. But every time once you come back, coming back from displaying the selected color by the user, coming back to the one of the colors, then you would have done it quite easily. But what I'm trying to make it, more funnier, more interactive, just to random. Okay. So initially, what I did is quite simple. RGB LEDs. I'll coming back to the RGB hardware part later. But anyway, you select any random number 1 to 40. It can be 1 to 20, 23, 24. Now, for how do you get all the color combination? I mean, if you want to make any color combination, for example, yellow, purple, you just type. There's a good site. RGB color combo of, for example, let's say olive. It gives you a certain thing. Okay, this is a color code, right? #8080. Okay, why 808000, Ravi? Because there are 3 colors, right? Each color corresponds to 8 bit of data. So in terms of pixel, can be represented in color format. For example, like. And we have seen 24 megapixel, 32 megapixel. Why? Because every pixel can be represented using 24 bits. In black and white, it's called actually grayscale. It's based 8 bit. Now it's 24 bits. So 8 bit for R, 8 bit for G, 8 bit for B. So 8080 means, of course, blue is off, and there's 8080 for the RGB. So 52% red, 52% green, and 0% blue. That's the actual hex combinations of the color. Now, if you go to the actual, the analog combinations of different color, for example, okay, like this, RGB decimal value is basically 120, 120, 0. So once you put 120 to R, 120 G, and 0 to blue, it will display a certain color called, let's say, olive. Okay, which is a combination of, I think, it's a mixture of greenish yellow or yellowish green, something like that. Okay, so these are the combination of the colors available in any international color sets. I think there's a good site I've seen. Canva actually. Canva it's a good one. You can you can get all the color combinations from there, like teal, olive, which are not, for example, let's say what I have selected over there. Once again, olive, maroon, teal. Yeah. Teal is the color, right? Like tea. This is kind of 008080. It's basically a deep blue-green color. Okay, and this is the RGB code 0, 120, 20. So no, presence of red is reflected. So a percent of 52% of green and 52% of blue, and the corresponding color of 0 and 120, 120. Now the question is that how do you provide those color or maybe those sort of analog values to the Arduino pins which are digital. Now see this tilt sign, these are actually PWM compatible, right? Okay.
Yeah.
I think you know, I think basic PWM knowledge do you have? I mean, like, do you know what is PWM and why it is called
pulse width modulation, right? So like it shifts the duty, it has a duty cycle based on the voltage what we are supplying.
But the why if I put high value of analog, high value of DC, why it will why it will, you know, it will I mean increase the brightness of LED or the speed of the motor and stuff like that. And once we put a low value of DC, it will do the reverse, because actually PWM is definitely pulse width modulation. The more the width of the pulse, I mean more the you should say the on time of the pulse, that means more the positive value of the pulse, the more the DC value will be applied to the I mean circuits or applied to the device. Yeah. This is the PWM. I mean, like, if you go to Arduino, I know that you know the basics, but still Arduino PWM. Yeah, that's actually a sign. I think, you know, I as of now I don't have this CRO with me. I have a digital CRO with me, so I could have seen maybe in the later half of the course I'll show you how actually, you know, this structure looks like. Actually, if you take a take a wire out of any Arduino PWM pin and feed it to the, you know, digital CRO, okay, once you know, keep on increasing and decreasing the analog values by applying this pulse width command, you'll see this waveform getting reflected on the in digital CRO. So this is 0. Okay, once we put analog right 0, why it is 0? Because the equation of any analog analog voltage coming from this input is nothing but tau by t into VIN. So basically V0 equals to tau by t into VIN. Now tau is what? Tau is on time. Okay, on time means obviously this one, the period on time. So on time by total time. So basically T on by T on plus T off. Okay. So this is nothing but tau by t. T is the total time period. Okay, this is the total time period. This is the on time, this is the off time. So sometimes on time is less than the off time, or sometimes the off time is less than the off time, right? On time. So on time by on time plus off time, okay, into VIN. So let me assume that once you apply, let's say the input voltage is 5 volt, fine. Now the on time is 0. Time period is basically same, right? T. So 0 by t into basically 5 volt is basically 0. Okay. Now coming down to here, this one. See here, the on time is basically, but on time is as good as the total time period for the entire time period of the cycle. So value is always 1. So for this case, on time is 0. For this case, on time is basically and the time period both are same. So tau by t is 1. So output voltage equals to VIN. Okay. But in this case, output voltage is 0 because V0 is nothing but on time by total time into VIN. Now the on time is 0, so output voltage is 0. Here on time is what? 25% of the total time period. So basically output voltage will be 1/4 of the input voltage. Okay. Yeah. Similarly, 50% means half, 70% means 3/4. In that way, you are actually applying more and more amount of, I think, analog voltage to be applied on a certain device once you increase this duty cycle or the on time. So that is the basically pulse width modulation. Why pulse width? Because keeping the frequency same, you are increasing and decreasing the pulse width. That means this on time. Sometimes on time is decreasing, sometimes on time is increasing. But the pulse period remains constant. Right. Yeah. That is why it's called
the average comes down.
Yeah, definitely. So the average value, yeah, that is the average value V0, that actually keeps on increasing based on the pulse width. Yeah. Anyway. So Arduino has certain pulse width compatibilities. Have connected, let's say 3, 5, 6, or 5 with R, 6 with green, and 3 with blue. So by default, we are selecting these 3 pins because we know that here RGB is nothing but any color is a mixture of all 3 colors. So definitely you need to put variable values to the LED. Now the value means the limitations is there because initially you see this color actually is 008080 because 8-bit number. What is the maximum number that can be represented in 8-bit Ravi? 255, right? 2 to the power 8 is 256. So total number is 0 to 255. Okay. In 4-bit, we have binary to the power 4 minus 1 is 15. Maximum number is 15. 1 1 1 1. Okay? Minimum number is 0 0 0 0. So total number we have 16, 0 to 15. Similarly, 8-bit we have a 256. Total number of combinations 256 starts with all 0. That means 80 to 81 to 81. So 81 means 255. Maximum you can put FF. That means 255, 255, 255. So so the value will never exceed 255, and that is why I am actually putting any value between 0 to 255 within this analog write command, because that is sufficient. So 0 means 0 volt, 255 means 5 volt. Simple. So basically, so you are putting different actually voltages to be precisely telling you that you are applying different actually values for the color. So just by applying different values, you are providing different voltages because of the pulse width modulation. Fine. So we are connecting. We have connected 3 inputs of the like green. This is green. This is blue. This is red to the 3 PWM compatible pins. 3, 5, 6. Okay. Now,
but how these others are connected?
Sorry, others means others. Okay, no. They are straightforwardly connected. For example, this blue. These are the blue, and these are the reds. And
center one, both are the same, like
same.
Connected to blue only.
Same.
Can you delete one line?
One line.
Oh, okay. It's a segmented one, right?
Segmented. I mean, it's like I'm trying to make it a LED strip. Normal neo.
I understood.
Right. So take a random number from 1 to 14, 1 to 15. Now that is up to you. How many random colors you want your design to be picked up actually. So let's say the NeoPixel have let's say 100 colors. So they're providing 100 random values 1 to 100. So I'm just putting 1 to 14. So it is printing the enter the color serial printed. Okay. So now while serial not available equals to 0, that is a precise tactics actually. That means unless and until user prompts any key from the keyboard, it selects any number, any random number from this color. Okay. So every time the control enters into the void loop with a different random value, 1 to 14, sometimes any number between 1 to 14. Okay. Initially, let's say it has chosen a number between 5. Okay, fine. Switch 5 or switch 1. Now I have actually have a let's say 14 cases for 14 different color, 1 to 14 color. That's nothing more than that. So we have let's say for one is basically red. Red is a red, yellow. Sorry, green, blue is very simple. Red means basically you put red high, all are low. Green is high, all are low. Blue is high, all are low. Next comes the combination of color. For example, yellow. It's a mixture of red and green, keeping blue 0. Okay. Next is aqua sand. It's a mixture of green and blue, keeping red 0. Next, orange. Mixture of red and green with a different one, not all 255, 255. Next, pink. Okay, now I've collected all this color from this Canva, right? I mean, selecting these colors and just by giving the voltage.
Understood.
Yeah, right. So magenta, navy blue, aquamarine, honeydew. You can add up as many colors as you want. So after that, after 14, I've just end up this loop. Now this is where the color is getting read from the keyboard. Meanwhile, it is displaying one of the random colors. You type something the way I've typed. Okay. Now there can be 5 words because G for gray, T for teal, M for maroon, O for olive, and F for purple. Now you can add up another colors, another words actually, another string. Okay. So once it gets a certain string, definitely it will take the corresponding combination for the gray, and it will let's say display the color for let's say 5 seconds. I'm just giving an example, 5 seconds or 10 seconds. Right. And then it will perform the same task actually. It it does nothing except writing the corresponding color values for the corresponding color to the different pins. Nothing like that. It's actually in software. We haven't called any functions. Everything is being done within the void loop sections. Okay. So it's kind of simple thing. You can test it out with your own RGB's LED. Okay, fine. Different RGB combination. If you want, something to be typed from the keyboard. If you want something to be typed from the, push button switches. I recommend you to come up with a unique actually solution that I want. Achha, do you have this OLED display?
Yeah, I have.
Okay, fine. There's a task. I'll tell you later. that let's say you have a RGB LEDs, right? One RGB LEDs as
Yeah.
well as a OLED. Actually, I've written the code, but anyway, I want you to at least to give a thought of that particular thing. What happens? There is a menu, okay, and what I want you to do that it displays the certain menu. For example, menus means something like that. Okay, for example, let's say your name and then value R, value green, and let's say value, let's say blue. Okay, then start. So we have a rotary encoder connected with the system. Okay, fine. So once you start, you by rotating the knob, actually your display. For example, this is the display. First comes your name, next comes the value of R, value of G, value of blue. So rotary, once you move the rotary encoder in the clockwise direction, the cursor moves, actually keeps moving from top left to down left. That is it. It is moving down. It is actually, you are actually scrolling down the display. So as you are rotating the knob, the cursor is moving down. As you are rotating in counterclockwise, cursor is moving up, right? Now, once you selected a certain value, for example, value V means green. Okay, value V means green. Then once you click the button, just means you press the switch of that particular rotary encoder, it selects that green and it will send a certain color value to the green, or maybe to certain color values to different LEDs to display certain color. Okay, in that way you can perform the same task what actually you have done here. This is automatically, it is manual. But as we are actually learning this rotary encoder, you have 2 days left. I just wanted to come up at least a basic solution. Okay, with OLEDs, or you can use your LCD also. Okay, that is your choice. And you don't need to go with an LCD or OLED, but OLED is a good.
I'll try with LCD.
Yeah, you can try the LCD. Let's next week we'll discuss with the LCD and then we'll move on to the OLED. Okay, I've already done both LCD and OLED. So that is a task. Same thing that we have done over here, but in a manual control. Okay, now you can have a few sections. Okay, unless and until user prompts something from the rotary encoder, it will keep on displaying all the random color. That is up to you. That you can do, that you can. That is not my intention. Intention is once rotary encoder comes into action, now you are just by moving the rotary encoder menu, keeps on moving up and down, up and down, up and down. Then once you select something by pressing the button, it will display that color, or it will showcase that color, or a certain, RGB. That is the task. Okay.
So
okay.
1 minute, I didn't get that. What is the task actually? So like 4 or 5 colors, it randomly scrolls up and down. If I select one, it has to display that color. You mean to say?
Yeah. There's a let's say that there's a 4, 5, 6. That is up to you. There's a this kind of menu over there. Okay. Okay. First of all, let's say the value of R, value of G, or maybe stuff like that. Maybe there are yellow, green, blue, something stuff like that. There are different colors. So that's the color-driven menu. The menu is basically a color-driven menu. So you are just moving up and down across this menu, right, to see what are the colors available on this project. Actually, let's say you have 10 colors available on the screen. You are moving up and down, and finally you have selected. Okay, I want to showcase yellow color.
Yeah.
At the moment,
Got it.
The moment you stop and you press the button, that means you have selected the particular yellow color. That is the, I think, the usefulness of the rotary encoder. You have a menu-driven. You have a switch which is acting as an enter button. And at the same time, you are having, let's say, up arrow, down arrow key kind of facilities just by rotating the knob in clockwise and counterclockwise. Okay. Next week, actually, I'll be having my Nokia display also, so we can have a lot more other complex menu-driven options also. Anyway, that you can start with there, and you can have this RGB LED. I just I'll just send you the code first of all. And I think this one thing that I also can share.
No, like it's just better to give him, like what you call this headings in a comment.
Okay. Anyway, that is up to you. Now, a very unique one that is what I trying to give you I think showcase you. That is a very interesting program. Okay, just a moment. Last year we have done some of these basics of Arduino, but this is what actually I need to showcase. So this is a very interesting kind of thing. Okay, based on, of course, Rotary Encoder and a. One second, yeah. First of all, let me upload and then I'll see. Just be. This is a very simple but really a different sort of program. To see the display.
Yeah.
So this is very unique kind of thing that we have a 5 LEDs that we have seen. Okay. So we starts with, let's say, white, blue, green, yellow, and red. Okay. So I have this rotary encoder, right? This one. Okay. So I just see you. Let me show you the basic thing. Once let's say I just put. Just a moment, actually. I think what is actually problematic. Yes, so the main intention is that we have a, let's say, 5 LEDs. Okay, 5 LEDs for different colors. For different colors, and we have a clock. Now, our intention is to, let's say, we have a clock at the 0th position. 0th position is basically white LED. So, if in the 0th position, if you press the button, it will turn on the white LED, and it will next time it will press the button, it will turn off the white LED. White LED. Next, if you move the clock 0 to 1. It selects a blue, and you can turn on and off blue just by pressing the button. Next, 2 means green, 3 means yellow, 4 means red, right? And similarly, counterclockwise direction. But what I'm doing actually that every time the clock means basically click, actually the rotate count that actually never falls short of 0, and it never goes beyond 4 actually. So 0, 1, 2, 3, 4 again comes to 0. So 4, 3, 2, 1, 0 again comes to 4. Fine. Okay. So just let me just connect the LEDs actually properly, because I need to connect the LEDs. I have actually had few operations with LCD. Now I am connecting all the LEDs one by one. Right. Just a moment. First comes the yellow one. Yes. 8. Okay, then we have a blue. 9. Then we have 10. We have 10. 11 and 12. Finally, we have. Okay, I missed out something. 8, 9, 10. Okay. Just a moment. Yes. Finally. Ah, 8, 9, 10, 11, 12, 13, right. So basically, just 2, 3, 4. Now you have seen the different conditions actually. Okay. Just a moment. Clock DT. Oh, acha. Fine. Clock DT. Yes. Yes. Fine. So, I think I have 8. Oh shit, 8, 9, 10. Okay, 8, 9, 10, 11, 12. Right. Oh. Yes. Fine. So let me begin. Okay, yeah. Yes, fine. So we have this encoder, right? I think probably yes, this Rotary encoder. I try to give you an idea. I don't know whether it's visible.
Yeah, now it's visible.
Right. Okay. I just this is I think, yeah, better. I think that will come up idea. Right. So 1, 2. I'm actually rotating the encoder. Yeah, 3,
Yeah.
4, 0, and I'm counterclockwise 3, 2, 1, 0. Right. For example, I am on the 0th positions. Or 0. So 0 means white C. So just watching that menu actually serial monitor menu. Say I press the button, let's say, and the white LED glows. Okay.
Yeah.
And see the white actually this one is 1. Again, say I press the button 0, white LED turned off. Now actually I'm on the white position. I slightly move to the 1. That is blue. Once I turn on the turn off switch of the switch, see the blue LED turns. And once I turn off the switch, the blue LED turns off. Similarly, green high and green low, right? Yeah. Yellow high and yellow low. Red high and red low. Okay. So this is the basic operation, but here actually I am slightly tweak the concept actually, and we have been trying to see which approach is good, whether interactive approach is good or maybe a different approach is good. I would recommend you to just take a pause and slightly go through the course, because it's not a massive one, but this could actually needs a proper understanding of which let's say input of rotary encoder needs to be initialized with interrupt assignments, and which are the normal input. And firstly, that see my LCD display is not flickering, right? That's the most important thing. We are actually just like you mentioned yesterday, that can't we display something as a stationary which does not change frequently. So I did the same thing actually. Okay, though I changed the LCD. Okay, I'll change the LCD only when it is needed. Okay, not every time actually the control is basically running inside the loop server. Okay, so this is basically the layout of the LCD that we need to be displayed on LCD. It can be LCD, it can be any display. So we have an I2C LCD, fine. It's a debounce deal. You know that we are actually using debouncing just to avoid bouncing effect. So next comes, see the clock now connected, rotary clock connected from pin number 2. And instead of rotary DT, that is the inverse clock, we have connected switch to the pin number 3. That means here number of interrupts are 2, right? One is the clock, second one is the switch. Button is also in the interrupt. Now we have two options. We can connect button at the interrupt. We cannot connect. We can connect the button as a part of the void loop program. So we have seen. We'll see both the operations actually. So there's a button counter variable for button count, rotate counter.
Now switch is to interrupt, right?
Switch is to interrupt, because 2 are 3 on the interrupt. Previously clock and decay the interrupt. Now we are putting switch in. This is basically experimenting to see which provides you the better, stable and better, good results in terms of your applications actually, right? So, right. So if you're, let's say, if it's not a switch, for example, in place of rotary encoder, if there is any sensitive, sensor or maybe device which needs to be monitored, which needs processor's attention frequently, it's better to connect at one of the interrupts without taking much of hassle of it, right? Because once you connect to the interrupt, what happens that the moment the condition is satisfied that you have written inside the interrupt service subroutine, the function will be called by the hardware, by the Arduino system. Okay, that's a thing that we need to do without having any physical intervention. So that is the thing that we have done. Anyway, we have the 2 variables, one for the button counter, one for the rotate count, and 3 different other variables, basically the button pressed and the rotated. So as we are not writing much of the program within the void loop, so most of the things actually have been written obviously from the program. You can easily figure out in the interrupt driven program, interrupt driven menu actually. So we have selected 2 variables, rotated and button press. These are the variables which will give the info of the Arduino void loop control. The rotator, rotary encoder has actually been rotated or not. The button is actually been pressed on. Okay, because the things are happening, the things are actually happening not in the loop, in the interrupt driven program. So it's an idea, it's some basic information to let the to let the Arduino program control know that this is happening. Because see, void loop does not know what is happening inside the interrupt driven program. It does not have any information. It does not call the program itself. Okay, it actually runs up all the statements written inside the void loop sequential. So whatever happens inside the interrupt driven service routine ISR, it will have no clue. So it's users or the programmer responsibility to let the system know, okay, this is happening, this is the results, right? So you take the results and you carry on after getting the results. So next time the interrupt occurs, you will put that results also. So this is why we have selected 2 variables, rotated and button press. Initially, both are actually it can be false. I think it's better to take rotated as a true, right? Because we are moving the rotation most of the times, right? Then we have a, this is for, you see these variable, I think you must have been familiar. These are all for the, what I should say, debouncing purpose, right? The last steady state, last speaker states, we have put everything high. We have seen this same example with a single push button switch and all. And yeah, fine. So this is another thing. So this is clock new. clock previous, of course, for a clock, we have a now variable, clock now state, we have a clock previous, we have a DT now, we have a previous DT previous, and definitely you have a time now, and time to for debouncing purpose. Okay. Now white LED to red LED. See, connected all are 8, 9, 10, 11, 12. These are the LED status. Fine. So, and initially all the status are false because all the LEDs are basically off, turned off. And this is the drawing of the LCD layout. Okay. I have come up with a very unique one that should be symmetric. That's in the first row, that is 0, 0. That displays this WBGBR, and this is basically, see, this is stationary. If you see my display, the first line remains constant, right? So it's better to put in a setup mode. So I have put everything in the setup mode. See, initially LCD.print WGGR by clock, set cursor 0, 1, 0, 0, 0, all are 0. So these two lines are stationary. So the change actually happens either at any of the 5 places. Of course, the clock keeps on changing based on your rotation, and either of the LEDs will be off and on. So either of these 5 fields can be 0 or 1, but as well as clock. Okay, not all the 6 bits will be changing at the same time. Okay, giving all the inputs. Rotary clocks, switch DT or input pull up, and then we have all the LEDs as the output mode, and then we are actually putting all the LEDs off. Fine. So these are basic, the basic stuff to be called. Now we take the initial states from the DT clock previous and the DT previous within the set of functions, because in actual program, in the interrupt program, we need to compare whether the present state or the next state both are same or not. Okay, fine. Now see here, interrupt, the first interrupt, which is a rotary clock, digital pin to interrupt, rotary clock, which is a pin number 2, or you can simply write down 0, comma, rotate. That means the corresponding ISR name of the ISR program is rotate. Okay. And it occurs for every change. That means every time you change your position of the rotary encoder, this ISR will be called automatically. But switch 1, also the same thing. Switch can also be changed from 0 to 1 or 1 to 0. Similarly, I have put this change button also here. Now it can be falling also. Falling means as you have declared the input switch as an input pull up, so that means whenever you press the button, the output is low, right? Otherwise, the output is high. Okay, you could have done, as a falling in place of change also. So time once is basically millis. Time once is a variable which starts after every millisecond. So time
we are not defining pin of this thing for that particular rotator button, right?
Pin of what?
Attach interrupt. You are
no. See, either you declare digital pin to interrupt. Actual pin rotary clock is already have declared pin number. Let's say 2.
Okay.
Either you declare in that way, that way, or you declare 0. 0 means pin number, and then 1 means pin number 3. Simple. Okay. There are 2 types of declarations actually. And the program, and that is why I have intentionally written this program, because in the other program you have seen like 0, rotate, change, 1, something. Now we are actually writing the program. Fine. So within void loop, anyway, these are various tried and tested experiments. So that is why this thing occurs. So actually you have pulled 2 programs. Okay, we'll see definitely some change. Maybe the result is different once we put the switch. Once you get the switch button section from the interrupt to the normal driven program, and that is why if I take the button from the interrupt out, then we need to write the code for the button within the loop, right? Not outside the loop. So that is also option. We'll see. But as of now, it is basically interrupt driven. So whatever comes as per the button press concern, it has to be written within the button pressed ISR. Okay. So loop, actually what it happens, it basically runs 2 functions. One is a print LCD, second is a button check. Okay. Now what is print LCD? We'll see. First of all, you'll see the print LCD. It's a very small program. Yeah, this one. Okay. This one. Small program, just a very single thing. It checks, first of all, if the rotated is true. If the rotated is true, then it actually LCD set cursor 12,1. And 12,1 is what? Because 12,1 means second row, 12th column, right? So if you see this entire our actually layout, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is that positions, right? So you can calculate what are the positions of just underneath the clocks actually. So it basically once the system comes to know, because everything is happening inside the loop, inside the interrupt. So while coming out of the interrupt program, you simply put rotated true or maybe button press true. So just by checking the variable rotated or button press, the system comes to know whether you have rotated the encoder or not. Once you have rotated, next you get the counter value from the rotate counter. Already everything has been there in the interrupt driven program. It just takes that value and simply prints that value and put rotated false. That means you are done with rotation. So every time a rotation is being detected by the Arduino, it simply prints that particular counter value of the rotary encoder 0, 1, 2, 3, 4 or maybe 4, 3, 2, 1, 0 to the corresponding position. That is the 12th column of the second row. That's it.
Yeah.
Without keeping everything constant. That means the first row and the first 11 positions of the LCD. Right. So it only changes.
Same, only the 12.
Only the way you have seen the 4, 3, 2, 1, something like that. Okay. Next, this program is happening. Next, it checks within the loop actually button checks. Okay. Now let me come to the button checker. Button checker is actually a program. So within button checker, it checks whether the button pressed is happening or not. That means if button pressed is true, that means you are in the, let's say, 0th position. That means you haven't rotated single this rotating now, or maybe you have rotated once in the clockwise or anti-clockwise. So rotation occurs and the value of the rotate counter, let's say 0, 1, 2, 3, 4, something like that. So within this 0 or 1 or 2 or 3 or 4, you have a one LED certain LED for every rotations, and every LEDs can have two states, right? 0 or 1. That means on and off. First it checks whether you have pressed the buttons or not. So if you press the button, that means you're intending to turn on and off the corresponding LED for a particular position of the rotation, right? For example, 0th position, you have a white LED, 1 position, you have a blue LED. So once you're in the 0th positions and you press a button, that means you are either turning on or off the button. So it first checks whether you have pressed the button at all or not. Once this is true, it comes to the switch case. And definitely the switch case, we know the switch case comes up with a sensitive input. Now the sensitive input was the rotate counter. The rotate counter simply gives you in which position you are in. 0, 1, 2, 3, 4. That means you are in the W, B, green, yellow, or red. So based on this rotate counter, we have, let's say, case 0, case 1, case 2, case 3, and case 4, right? Because we have only 5 cases. You can actually increase up to other cases if you have a, let's say, 20 cross 4 LED or LCD or maybe other displays which actually provides you more space actually. So just by understanding one case, will be getting all the cases. For example, we are in the case 0, first case. That means we are in the white LED. Okay. Now we are checking whether the white LED status is what? False. Initially, all the LED status are false because we have turned off all the LEDs. So definitely white LED status will be 0, false. So if the white LED status is false, put the white LED status is true, and you are turning on the LED just by putting high over there. Else, that means white LED status is true. That means you have pressed the button before that and turned the blue LED, white LED on. Now, once you have pressed the button once again, keeping the position 0, that means you are in the 0th position. That means this time you intend to turn off the particular LED. Okay? So white LED initially was false. You put the true. Else means actually you are in the true section, so you are putting the LCD status flow and you are turning off the LED. So every case we have 2 positions. Okay, case 0, 2 positions, case 1, case 2, case 3, case 4. So every case, first it checks the corresponding LED status. If it is false, it turns on the LED and put the LED status as true. If the white LED status is true, that means you are intending to turn off the LED. It turns off the LED and it puts the corresponding LED status false. And after doing this thing, what it does, you need to change that. That change needs to be reflected on the LCD, right? Okay, the LCD white value is 0, but once you are turning on the LCD, the W needs to be converted to 1, right? Okay, so it just checks that one. LCD cursor 0, 1. 0, 1 means first row. Second row, first column. Second row, first column is what? That is just underneath the W, this one, okay? Just underneath the W. So just underneath the W, it changes the whitelist status. So if it is initially 0, it changes to 1. If it is initially 1, it actually changes to 0. That's it. So see, I've actually what the significance of the code is that I have tried to minimize the use of LCD just by writing few statements. See, every case there are only 2 statements. That means every case is it actually modifies the corresponding LED status only, keeping all the 4 LED status same. It does not alter or affect or modify all the 4 because all the 4 status are same. You don't need to change every time because you are changing one LED at a time. So the LED which are changing its status needs to be reflected on the LCD. That's it. For every case, see, we have a 2 LCD command. We are setting the cursor. 0 means 0, 1 means second row, first column. 2 means actually third row, third column actually, first row, right? So we are in the blue. Next we have a 4, 1, that is the green. Next we have a 6, 1. Next we have a 8, 1. So basically up to 8. So basically what happens? 8, 6, 4, 2, 0. These are the 5 LEDs position, right? So let's say 0, 0. That means this is the position of W, right? Okay. Okay. Hello.
Yeah.
0, 1 means what? That is the value of the W. Okay. Similarly, the LCD cursor 2, 0 means the position of the word, the letter called blue, and 2, 1 is the value of the blue. That means just underneath that blue. Actually, we are actually considering the second row. So simply we are just keeping the thing simple just by writing less amount of comments corresponding to the LCD. So that is the basic intention of the button checker. Button checker does nothing but to showcase or to reflect the changes happen to the corresponding LEDs. Okay, just by pressing buttons and check. Rotating the rotary encoder. So it does this, and after doing all
this is only to display one or 0.
Only to display right? Your thing in either LCD or OLED. And once before coming out of this function, it changes buttons to press false because you are done with that. So you haven't changed. You haven't pressed the button, so button press again becomes false. So it starts with the button press 2, and it ends up by putting it false. So once it comes out of the button set, so that is the end of void loop. Void loop does not. Void loop it does nothing apart from these 2 functions. Now the question is that what about the rotary encoder and what about the button press? Now coming back to that, so rotary encoder we have a ISR called rotate, and we have another ISR called button press for the button. Okay, so rotate is different. Button press, you know, this similar this debounce program. Again, we'll be back to that. Now rotate, that's a actual program. See, we have used the same logic. If you can, I think, go through our previous program also. For example, let's say rotary encoder in chapter also rotary encoder. Yeah, simplify. Here also rotary encoder. Last day we have seen. So this is our update encoder. What you have seen, we have actually taken the current state clock from the digital set. We have already taken the previous state of the clock and the DT within the setup function, right? Here, this one, right? Clock previous and DT previous. Fine. In the loop portion, this interrupt portion, again we take the value of the digital just by reading the digital read command for the rotary clocks in the clock new. Similarly, we have done same thing over the current state clock. So we are using the same logic. If clock new not equal to clock previous, this one, and the clock state equal 1, and the clock new is 1, that means you have actually turned your rotary encoder either clockwise or anti-clockwise, and again you see if the digital read rotary encoder not equal to clock new, rotary encoder plus, else rotary encoder minus 1. That means basically you are in the clockwise direction or in the anti-clockwise direction. Okay? So if these are not equal, it is clockwise. If these are equal, this is basically not equal, it is clockwise. Equal, it is counterclockwise. And every time the modification, what I haven't done over here, it is basically if the rotate counter greater than 4, keeps it actually keep it 0. If it is actually -1, that is less than 0, keep it 0. So it will ever go beyond 4 or maybe 0. So keeps on moving 0 to 1, 2, 3, 4. And we take the clock previous equals to clock new and rotate equal to true. Just coming out of this rotate function, as we have started with the rotate equal to false, we have tried rotate equal to true. Because if the rotate equal to true, then within the loop program, while running this print LCD command, your void loop control comes to know, okay, rotate it equal to 2, I need to modify this 12-1 position of the LCD to reflect that rotate counter, maybe 0, 1, 2, 3, 4, whatever. So that is the, I think, void rotate command you're seeing. And then a button pressed actually simple. I think, this command we have seen, right? This is the debounce command. Okay. I think we have seen the debounce command in the last couple of programs also. Same command over there. Just we have written everything inside a ISR. Okay. That means you have taken finally the current state value, and if the millis minus debounce greater than debounce greater, then it comes to the, it gets into the loop and it checks two things. Okay. One is if the steady state is high, initially steady state is high, and the current state is low, that means button has been connected in the input pull-up mode. So definitely current state should be low if you press the button. That means button pressed is true. And serial print button press properly. Otherwise, button press is false. So just obviously, because you don't need to check the button press false, already automatically it actually gives you the button press false. Okay, let me okay. Just let me take that. Yes, ठीक है. One. Okay, fine. Right. So, and then we take the current state into last state. So that is basically same, right? Now you can put this entire thing, inside the void loop also, right? So just by activating this, this command actually. So if you want to put your switch program, the button program within this, void loop, so you need to get rid of that statement. Okay, that's rotary switch statement, because if you put everything regarding switch within the void loop, this command no longer remains valid because you haven't connected rotary switch as an input mode. Interrupt mode. Okay, fine. So in that case, you uncomment out the line actually. So the very, very simple way of obviously I just sorry. Connection is quite simple. It's it's for a beginner, and for the people like us, to get started with all such menu driven programming, it will be very helpful. I've seen, and I'm trying to get us simple solutions for you, me, and everyone, just to make sure that actually less effort will provide the much amount of fruits, right? So this is a good one. You can try it out, and you can actually come up with your OLED solutions of RGB, right? What actually we had actually discussed just before that. Okay. If you have a OLED display, you can come up with the OLED, or maybe if you have a LCD, you can come up with LCD. But I prefer to go with the OLED, because OLED actually, the OLED is much more wider, than this LCD. Okay, LCD can have only two rows, but OLED you can have, let's say, multiple number of rows. You can keep on, playing with all such options, and then just by pressing the button, you can have the corresponding value selected for the options. So this is the advantage of OLED. One more thing that I need to cross check. I just this one. What? 1 second. I think Ravi, you must be knowing about autonomous board, and you have made some different boards also, right? Like autonomous or maybe manual.
Manual I made.
Okay. What we do actually, my students actually, some of my students, they're planning to make a autonomous board. Okay, under my guidance. So providing all the documents, and see, I have this Autobots. There's a mail actually. The name of it's basically Autobots, right? So okay, no, this is not Autobots. Means this one Autobot. Right. There are few attachments. See, how I mean, do you, I mean, come up with IRs and, HC04 and maybe PIR sensors and how the IR works. And these are the basic footsteps of autonomous board. Let's say you have a white board and you have a black lining over there.
Line follower.
Line follower kind of stuff, right, left, right. And we have a 8-channel boards also. You can actually help you to come up with a very good solutions. And then we have a, let's say that is our college tax actually. And this module actually helps you understand, what are the basic things to be, needed to make a first autonomous board. We have a chassis, we have a wheel, you can have all such things, you can assemble them. We have a small video and we have actually provided everything line by line, how to connect, okay, all such things with DC motor and the motor driver also, right? L29 with a bridge sections, with a bridge.
I got LM298.
L298 or L293, both are same. Okay, 298 is the most stable one. Yeah, how to connect all such things. The basic one. Intention was to control the motor automatically first. Secondly, using IR remote. Thirdly, using Bluetooth. Fourthly, using Wi-Fi. And fifth, of course, after a certain time, with certain ML command, machine learning command. So this is the basic board. I think I've shared the mail with you, and we have a DC motor. How the DC motor works with all the connections and all. Okay, let me share this mail with you first of all. Just tell me your mail ID.
RAVA.
R?
VA. VA.
BA. Acha.
VI. Vanilla India.
Acha.
Vanilla.
Acha.
Vanilla
So it's
no, what I meant to say RAVI. I'll text
RA?
VI.
Acha. VIA.
I'm texting in this thing.
I just.
You can copy. Chat box I texted. I texted chat box.
Okay, chat box. Okay, sure. Sorry. Yes. Okay. Okay, RFI, so 5098. Okay, fine. So we have selected. We go through this. We have all sessions. Anyway, so definitely, I think I mean, maybe you have heard about the IR and those L29, L293D and all, right?
IR, I heard about it, but I didn't work with it.
Okay, fine. For example, now if the DC motor, how the DC motor works, everybody, I mean, you should know better than me and what are the three things, but how do you connect the DC motor with L293, L29? I think you know, or maybe you don't have any prior experience.
Prior experience I don't have, but have that circuit. I've seen that in that positive, negative.
That is true, but L293D or maybe L298 is a IC actually what I have also used over there. When you must have seen, I think this one the last time. This is what I made recently for a small demonstration purpose. Quite pretty simple actually. That you have an IR remote with you, right? The basic IR remote, and as a basic IR board actually. So what happens? See, let's say if you start simulating it, see if you put the this up arrow key, it will turn in the forward directions with a high speed. See, this is the high speed. Okay, you can speed up also just by increasing the volume button also. See the speed up, and you can speed down also. And you can move the motor in backward direction. See, this is the negative. The speed actually negative. Okay, that means it is moving in the rotating in the different directions. Now, if you press that, let's say this button, right button, you are turning the motor in the right direction just by putting the left motor on and right motor off. And if you are pressing this one, that is basically turn left. Okay. Yeah. basically simple model using the L298 module actually, right? So or L293 module actually. So what is a module is all about is quite simple. Module actually consists of a hay bridge. Hay bridge means one L293 provides the necessary connection for two motors. Okay. So what you have, if you go through this motor can have two things. One is the input coming from the Arduino, which are not sufficient to drive the motor. Of course, this motor are maybe 12-volt motor. So we need to provide a corresponding 12-volt supply. Although the Tinkercad does not give you that amount of information because they are 5, 12, both are same. So don't get confused about all such thing. But in actual life, you need to provide separate supply for L293. Okay, from battery or maybe from eliminator, maybe from the battery and power bank. So this is a VSS motor supply. That must be 9 to 12 volt along with the ground, 4 grounds. And this is the internal voltage 5 volt that you can provide from Arduino, or you can provide from the battery itself. So it has two inputs for the first motor coming from the Arduino, and it provides two output for the motors, okay, which will drive the motor either in forward direction or maybe in the reverse direction. Similarly, this is the left hand side. The right hand side is similar for the second motor. Okay, for the second motor, you have two inputs coming from the Arduino. That means the command to be given to the motor to rotate let's say forward, or to move backward, or to turn right, left, stop, speed up, speed down, and stuff like that. So these inputs B1 and inputs B2, or inputs A1, inputs A2, these are coming from the Arduino. Okay, and output A1, these are the sorry, signals provided by that module L293 to the motor. Similarly, over here, output B1, B2. And we have a enable 1, enable 2. Now, what about this? The motor can have at least, the basic two information to provide. One is the basically turn on and off and just to rotate the motor. And second one is the speed of the motor, right? Now, the speed of the motor cannot be a 0 or 1. Speed can be maximum, can be minimum, can lie in the middle of minimum and that. So it should be definitely a PWM value. It should be analog value. Okay. So what you are doing, you are actually using two analog inputs, analog pins of the Arduino, to be precisely saying, to provide the varying speed, or to provide the variable speed to the L293 to the enable 1 and enable 2. So enable 1 and enable 2, if you are rest assured that you are moving the motor to the highest possible speed, then of course you can put the enable 1 and to the supply voltage plus 5 volt. So it will always take the maximum voltage and it will put the motor in that speed only. But if you want to vary the speed, maybe sometimes you slow down and sometimes you speed up, then it's better to connect this enable 1 and enable 2 to the two enable inputs of the Arduino. That's a key point. And how it is providing this connections, quite simple. This is basically a hay bridge. And this is there's let's say the motor, and there we have let's say 4 connections for every part. We have a 4 connections. So let's say this is the connection 1001. So basically 1010 motor moves right. So let's put this is 1 and S2 is 0, S3 is 0, S4 is 1. So basically motor is the connection is complete. It's just like that. Okay, this is like that. Sometimes it is, sometimes this is. So basically what happens, if the motor is rotating this way, it is basically, if it is forward, then definitely it is backward. And if it is forward, if it is backward. So basically the same motor, just by changing the polarity, the motor can be, rotated in the reverse direction by changing the polarity. So we are doing the same thing for having this H bridge on the L293. So we have a 4 op-amps for the 4 L293, and we have a connections like that. Okay. So this input 1,
this one input 1, input 2, input 3, input 4 are
Arduino
digital pins.
Arduino input, digital pins. Enable input 1 and enable input 9. These two enable inputs actually. These are the PWM inputs, right? This one, enable 1 and enable 2. Enable 1 for motor number 1, which controls the speed of the motor 1. Enable 2 is which controls the speed of the motor 2. So these two are the PWM inputs.
Total it contains 6 pins.
Yeah, sure. Any PWM enable 2. The rest of the 4 pins are basically digital inputs. Then you can have a lot of pins, and these 2 pins you can connect motor in that way. Okay. So similar thing, I did the exactly same thing. See, this is the enable pin. If you can see, it is the circuits actually. First pin and the 9 pin are the enable. So I have connected this first pin actually to one of the enable pin parts 5, and 9 pins also we have connected another 6. So 5, 6, these are the PWM enable pin. And rest of the pins, for example, this one and this one, and we have another 2 inputs like this one and we have this one. So these two are basically normal pin. Normal pin PWM, that is not a mandatory thing to be. That is up to you. But of course, these two pins, this 1 and 9, that should be connected to the enable pin. Okay, that's the first and foremost thing. Second thing of the project, that is the precise thing, that it's an IR remote control place. Now, what about what do you mean by the IR? Infrared frequency. Now, infrared is what? Infrared is basically, after visual spectrum of light, which ends up at 700 nanometer, the infrared starts, and it can, you can subdivide IR into three parts. One is the near infrared spectroscopy, which is a topic of, this is a research topic, the point of interest of research topic of today's healthcare research, and me too also, because you have seen the NIRS based different spectroscopic method to detect the blood glucose in a non-invasive manner. So you don't need to prick, any injections or any, that needle to get the blood out, and then to see, okay, what is the glucose level and what is the insulin level, stuff like that, right? So the NIRS based spectroscopy, there's a very good device also, NIRS based Texas instrument. I think I'm not wasting your time, right, Ravi?
No.
NIRS based Texas instrument. I think this is called mobile Texas instrument device. The name is, I think, what is the name? Neo, I think. Texas instrument this device. Okay, let's try. DLP ultramobile. This is one thing. This is this one. Yeah, TIDA is a nano scan board. See, and this is a very interesting module, and they have just developed that thing. It is in the research purpose. See, we have different biomarkers present in our blood, right? Sodium, potassium, and other proteins, and those biomarkers have a different wavelength versus absorption spectra. That means the wavelength of a light bombarded on your skin actually that penetrates your skin, and that might interact with all such biomarkers present in the bloods and all body fluids, and their waveforms actually get scattered, right? And this scattering effect, okay, this waveform, wavelength versus absorption spectra provides that there's a one-to-one relationship between this NIRS spectroscopy on NIRS based waveform as well as different biomarkers. So what can happen just by bombarding, just by incidenting the light on your skin, you can do what? You can let this light interact with different biomarkers present in the blood, for example, glucose, hemoglobins, and stuff, and it can provide different scattering effect, which can also be reflected to the NIRS receiver to see, okay, this is the blood position, this is the blood glucose position, okay, or this is the hemoglobin status, or this is the oxyhemoglobin status, right? One thing we have seen in case of pulse oximeter technique, okay, the PPG method, heart rate, okay, that fingerprint based PPG, pulse plethysmoscopy technique actually, which basically provides the infrared spectroscopy. Infrared is basically a part of near infrared. Now they have come up with another good solution that's called near infrared. The near infrared region from 700 to 2500 nanometer, they have seen that significant I think scattering effect between those biomarkers and this different lights of different wavelengths. And we have different LEDs also, which provides the light of NIRS wavelength. We have an NIRS LED. We can search it out. It's a bit costly, but NIRS LED also there. I have tried with few one actually. NIRS LEDs, IR and NIR LEDs. So they have some of the companies actually they have manufactured that NIR and IR LEDs. See, 700 to 1400, 1400 to 3000, 300 to 1 nanometer. So these are the different region of the IR. As I have mentioned, this is the one is the IR in near infrared. Next comes the mid infrared. Next comes the actual infrared, the deep infrared. Okay, so as we are moving from 700 to 1400, 1400 to 3000, see, we are increasing the wavelength. It means that we are decreasing the frequency. Okay? So as we are moving towards IR2, NIR2 mid, so basically we are increasing wavelength means we are decreasing frequency. Okay, so that is the different, variations of that. But anyhow, IR is what? Actually, IR is something. IR. infrared actually, sorry, Indian Railways. We have a very good document just like that. Okay, let's see what such things. Yeah, this one actually. Yeah, you can understand from this point actually. So in IR sections, two types of IR LEDs or IR actually observed. IR is basically infrared radiation. You know that as a part of the electromagnetic radio spectrum, or maybe spectrum of this that EMG wave, which is the non-visible length between 700 to 780 nanometer to 1 millimeter, right? So it is categorized into three parts. So we are normally into the first part, 780 nanometer to 1.4 micrometer. Okay. Hello.
Yeah.
Okay, fine. So, and we have a different LEDs to that. Now, your phone camera can actually identify the IR LEDs. Okay, I think you have seen some of the shopping malls have provided malicious interpretations of putting camera in their in the female change room, right? I think it's available. So just to check whether they're doing any bad practice or not, just put your camera on. Okay, just set it just behind the mirror. Actually, we can have an idea why there's an IR camera is available now, because all CCTV cameras are IR enabled. So if you can have an IR LED, you turn it on and just you turn on your mobile camera, it is visible. It becomes visible to your eyes actually, but it's not visible in our eyes because it is out of the visible light spectrum. So we can have camera also to see the LEDs on or not. So anyway, so the intention of all such robotics or maybe IR based application, for example, even remote is basically what? Remote is actually by pressing every key, it generates a certain hex value. And these are the standard hex value provided by the International Consultative Committee of Telephone and Telegraph, CCITT, for different IR for different buttons actually of an IR control remote. So IR remote or maybe any IR device that can be your mobile phone also. If your mobile phone is a MI or maybe OnePlus, it might have an IR blaster. So yeah, that can be used to turn on and off your AC also, maybe microwave and stuff. All are universal, and they are actually providing the same code. That means right arrow means 5x5058 FD101F. So these are the standard codes available for every buttons and every other other buttons apart from this alphanumeric values also. Again, this is said by the standard committee. So IR remote actually provides that with those values. That means IR remote definitely at the flag end here also, the IR remote is what? IR remote is nothing but a microcontroller based applications where there is, once you press the button, that means just you press a button, push button actually, and it generates a code from the microcontroller and it sends the code through the IR emitter or the IR transmitter. Okay.
Yeah.
Okay. So it should have an IR transmitter. So definitely, if you want to make a board which is IR remote control, it should have a IR receiver to be installed over there, right? This is IR receiver, and you have a TSOP IR receiver. If you see that, we can write down TSOP, yeah, both 1738 or maybe 3218. This is the IR receiver model. Same concept. Okay, 3-terminal device. You can get it from anywhere. It's quite cheap. I've actually 2 years before I had purchased 10 pieces of that, maybe it cost around 150 200. So it's quite cheap and you can use at any applications, not only over there. So IR receiver is receiving any IR actually pulse generated by the remote control by any other IR transmitter also. Okay, and this
it detects light or the frequency of this thing?
Definitely it's a frequency. See, frequency is nothing but a light. If you provide a frequency, if it comes,
it can be radio frequency also, right?
You can have a radio frequency. For example, your mobile phone generates a radio frequency. Once the way actually you are calling somebody is calling you. Once the call gets detected, it is basically providing the frequency in the radio range. Now GSM range is 970 megahertz to, let's say, 994 megahertz. The band is different. I'm giving you a small example that all we are familiar with FM, frequency modulation, right?
Yeah.
Now the question that might pop up in your mind that the 90.3, 93.5, these are all radio stations centered around a certain carrier frequency. Somebody is a 90.3, somebody 93.5. Why? Secondly, every FM frequency is providing, for example, somebody is providing SP Balsubramaniam sons, someone is Yeshuda, someone is, let's say, providing a documentary or something. Someone is providing audio story podcast, and some channel somebody is discussing about social issues. But anyway, the audio frequency, what is the audible range? I mean, what is the audio frequency range? Not 20 hertz to 20,000 hertz. It's 300 hertz to 3.4 kilohertz. Actually, the range that we talk, that you talk, me also talking to you, also talking to me. Sometimes once actually me and I become so much aggressive, right? Our voice gets a shrill effect. Then the frequency increases. For example, if you hear Chitra, Lata Mangeshkar song, their frequency is quite high because they are actually sound as a very quite high pitch level. Okay, like Tum Bin Kiya Jaye kind of song. But let's say the low pitch level, the of course frequency is quite low. So normally the telephone bandwidth or the mobile phone bandwidth for any permissible audio frequency is 300 hertz to 3.4 gigahertz. So with a bandwidth of 3 kilohertz. Fine. So 300 hertz to 3.4 gigahertz. So channel 1 is providing channel 1 is providing in FM is providing a program which is basically somebody is talking, or maybe somebody is singing or stuff like that. Frequency is same, right? Because I'm talking also the same frequency, you are talking also the same frequency. So all those stations, FM station 5 to 6 stations, let's say, which are located at Hyderabad or maybe some other cities, they are providing same. I mean, they are actually using the same frequency to generate or to produce their program. But why everything actually are getting on aired? Okay, it is in the air. Okay, you are airing the program. They will not interface with each other. Why? Why the 98.3 FM? Sure.
Because of different frequency.
Different frequency means, but your voice frequency are same. Audio frequency at which some song is being performed or some podcasts have been, broadcasted, they are same. Mostly same actually. Yeah, you can say that some stereophonic sound that kind of have a different frequency, but which are not at all distinguishable actually. They are quite same. Actually same. It's called a baseband spectrum. The baseband spectrum is quite actually same. Whether you talk, whether you give a running commentary of a cricket match, or you are podcasting something, probably all of us are using or are actually speaking in the same frequency, right? Not in the same accent, but the same frequency. But why they don't interface with each other? Because of course you have actually you got the correct answer, because of the carrier frequency. But how the carrier frequency comes? Because I'm talking in the range of let's say 3 kilohertz, maybe 1 kilohertz. So 1 kilohertz to 98 megahertz. This shifting of frequency is called a FM, frequency translation. That means frequency translation from audio frequency to RF frequency. Okay, this is a RF, because 98.3 megahertz is it no longer remains in the audio range. This is the RF. So every time, so that is also generating a frequency, but that is again, this is a frequency which does not, this frequency, is not visible. This frequency is not actually audible. Also, if I talk in 98.3 FM, you can't hear it actually. Probably I won't be able to talk in the 98.3 FM also. I mean 98.3 megahertz also. So these are not audible range, but they are providing a upward frequency translation from the lower frequency to the higher frequency. And action is actually, advantage is twofold. As you are increasing the frequency, that means you are providing the high energy also, right? Because energy equals to h nu. So the more the frequency of the signal, the more the energy of the photon, right? Involved within the particular signals. So you're providing the high energy, and you are providing the necessary amount of energy to travel across a certain amount of kilometers. And that is I think the beauty of the FM, that as well as the blessings and the curse. Blessings is what? Blessings is the sound quality is massive. It's quite good as compared to other radio system, for example, AM, shortwave, medium, and all. But the curse is what? That its communication coverage area is limited. You cannot get the signal FM once you come out of this city, right? Maybe the signal becomes feeble, signal is getting faded out. And the most interesting part is 98.3. This signal, at the same frequency, we have a different station at West Bengal, at Hyderabad, at Karnataka, at Kashmir, and all. Why? Because it's called a frequency reuse. They are reusing the same frequency because the blessing and the curse actually becomes blessings because the communication area is limited. That means you know that 90, if I use 90.3 in the Hyderabad, so out of the Hyderabad, this 90.3, this band actually no longer valid, actually remains valid. It varies, but no one is transmitting something. Somebody is transmitting within the Hyderabad, it is limited to Hyderabad. So if I am in the Karnataka, if I am in the Kerala, I can use the frequency to broadcast my program. So 90.3 corresponds to Kerala. So the frequency remains same, but the program are different. That is the again beauty of the different. So anyway, these are the radio frequencies generated by the system. Similarly, IR is also radio frequency. Now, radio frequency, every frequency should actually carry energy. Now, why the energy transmission, energy transmission occurs, when somebody is providing any energy and you are receiving any energy, that is also visible if you have this equipment. For example, you can't see X-ray, gamma ray, and beta ray. But if you have an X-ray plate and if you have a special arrangements, then it is visible. It actually becomes visible to you. Okay, this is X-ray penetrating your body, and finally, before it comes in collision with a different bones or maybe other stuff, foreign elements. So this is the arrangement. So you need to provide the corresponding arrangement to make it visible. Otherwise, in our naked eyes, we can't be able to see that because our range of frequency is different. It is up to 700 nanometer. Our IR starts after 740 nanometer, but it is visible once you have a special arrangement like camera. Okay, so this is one kind of thing. Secondly, in the motor, actually, what you have motor, you need both IR transmitter and IR receiver. If you want your motor to be automatically controlled, that is autonomous bot means what? Autonomous bot, this is not an autonomous bot. Probably people might prefer to call it as an autonomous bot, but it's not an autonomous because you are providing manual commands. Okay, it will not rotate unless and until it actually receives any command from the IR remote, or maybe from Bluetooth based app, or maybe from Wi-Fi based app. Okay, so it's something you can say manual control. But if you want everything to be controlled automatically, if you make it a semi-automatic, that means the motor starts rotating and it actually it finds its own way, right? Without having any physical intervention. Probably you can have certain special feature also. You can provide certain commands. So if you want to stop the motor instantly, you can provide a certain command from here, it stops. But everything should be controlled automatically. Then your motor should have both IR transmitter and the IR receiver, or certain area. For example, this one. So IR is what? So any IR module actually comes up with a IR transmitter and IR receiver, which is also a photodiode actually. So maybe some other IR receiver also. So IR transmitter transmits something. So if you have a reflective surface, it comes back to the IR receiver and it gets reflected. So if there is no reflected surface, there is no obstacle. So how does the system come to know there is an obstacle? Just by turning on the IR and just by receiving the light, whether there is an obstacle or not. So similarly, see, this is the same thing. There's no obstacle and there's obstacle. Okay, so this is how this IR actually occurs. And line from the line follower to a special application. For example, if you have a right sensor and the left sensor, this is stop. Why? Because all the sensor on the black parts, or probably there's a white lining on the black parts, or there is a black lining on the white parts. So if your car is something like that, they both the sensor are facing the black ones. Black one is basically we're actually symbolizing it as an obstacle. The motor stops. This is what? This is basically turning left means basically your motor is on the right sensor is on the white path, left sensor is on the black path. So it needs to be turned left just by. So if you have a car, if you want to take a turn left, you see the left motor, left wheel momentarily stops, and then right motor takes a turn, and then both the wheel starts rotating to take it to the left level. So similar thing happens with the right. So that is why one of the sensor is on, one of the sensor is off, and it takes a turn left. Similarly, turn right is that. Turn right means basically that light sensor on the obstacle or maybe the black path, and left sensor on the white path. So if this arrangement happens, so the system will automatically understand that we need to turn right or left. But here, everything is actually has been controlled by the IR. The system does not have any automation. Any automations or any automatic commands to be controlled. But that is the difference, nothing like that. So maybe moving forward, moving backward, you have a different model actually. So we can have a lot of arrangements and a lot of implementation of the same thing. So this is simple IR controller. But again, I have actually, I think this is the code, or maybe I can provide after the after the meeting, I can provide the Tinkercad link also. You can have, I mean, if you have an off time, maybe in the next week we have a different kind of IR controlling mode that probably. Yeah, we have an IR remote, but there's an IR module connected to, let's say, this two wheel, right? This two wheels, and you want the motor to be controlled to a certain extent automatically. So the automation comes, and then you have a semi-automation. That means you can start and stop at any point of time. So that comes the first priority. But once you start the start simulation button, it will turn on, and it will, let's say, it will have turn motor in the right direction or the left direction based on the obstacle. So how do you provide the obstacle? Just by providing an IR transmitter over there. So IR module, if you just place cursor over there, it will generate a certain obstacle. So once it comes to know, once it detects an obstacle within its close vicinity, it will turn the motor in other directions. Okay. For example, right, left, right, left, left, right. So that can also be done. So similarly, I think I think this one. We have also another one is this is also very simple thing I need to showcase you. Using PWM count, we have seen to I think to change the brightness of the thing. Similarly, we can increase or decrease the speed of the motor also. I have just sharing the thing. By the time it opens up. Okay, so this is again a simple discussion. This is deep switch. Deep switch is what? Okay, if you can type deep switch. Deep switch is the split of 4 switch, right? You know the deep switch is actually similar thing, same switch, but for example, deep switch 2 parts. So one part has to be connected to the supply. Another part has to be connected to the ground with a biasing resistor. So this is basically pull down resistors, and the value of the resistor, I think I have taken 1 megohm. You can take 10 kiloohms also, 100 kiloohms. So 1 megohm. So initially, if you let's say read the value from the switch over here, definitely from 1, 2, 3, 4. Let's say this this is for the fourth. This is for the third. This is for the second, and this is for the first. This is for the first, right? This is for the first. I think push. I mean deep switch, right? So see, if you read this switch over there, every point is connected to the ground with a particular resistance. So definitely you will get a 0 voltage. Okay, because you have pulled down every point to the 0. This. Once you just shift this position, the switch from this 1 to on, off to on, particular switch actually gets turned on, and it will provide a 1 to the corresponding input. Just opposite to input pull-up. Input pull-up, we are getting low when you press the button. Here, we actually were getting low when you press the button. That's it. And you have a simple oscilloscope kind of stuff to see the waveform of the nature of this PWM, and you have a DC motor. The intention is that once you turn on the device, it will rotate the motor to the highest speed. High speed, matlab, you are providing 255 as a speed of the motor. Okay. Yeah. 250 means highest duty cycle, 100% duty cycle, and motor is rotating with a high speed. Fine. Now, once you put this switch on, the duty cycle is 25%. Sorry, 0, 25, 50, 75. So these are the conditions. See, these are the code. Quite simple. 2, 3, 2, 4, 7. These are the input. 8, 8. So 8, 7, 4, 2. These are the 4 inputs, and motor we have a PWM input. Okay, this is the PWM input. This is the PWM input. Plus sign has been connected to the PWM input, and we have also this one and ground one connected to the oscilloscope just to see the nature of the PWM curve. So we have 4 inputs, and we compare. If A is high and all are low, that means duty cycle is 0. So you are putting 3, 0. That means that will turn off the motor. If A, B is high, all are low, it is putting 64. 64 means what? 25% of 256 is what? 64, right? Yeah. So that is the duty cycle is 24. 50% of duty cycle is what? 128. When C is high, this C is high and all are low, it is actually providing the motor with a 50% of speed. Then when D is high, all are low, it's providing 198 is basically 75%. And if else is basically, else means once you turn on the machine or turn on the actually simulation, it will turn on the motor with the highest possible speed. That is basically 355. Similarly, you can see. Yes. Yeah, right. Start simulation. See. Initially, motor is rotating at the high speed. See, 555. Duty cycle is 50%. And then see, it becomes 5 volt. That is the highest possible range. Right.
Yeah.
So let's say I put the button 1 on. See, duty cycle is 0. It becomes 0. Then again, I put it off and I put it on. See, 1 is on. See, that is the duty cycle, 25%. See, the on time is very less, right? On time is very less actually. Mostly these black portions are actually off time. On time is very less. That is why duty cycle is 25%. Now we take it off and we turn it on 50%.
So what if we combine 2 and 3? So it becomes 75, right?
No, actually, yeah. Let me just clarify. I think no, it is actually providing 100 because for all the other combinations, I am providing high. And if 2 and 3 high, okay, that is up to you. Okay, but I thought that okay, we are selecting one switch at a time. But if the combination is if 2 and 3 are high, you can change the duty cycle too. But apart from at a certain switch condition, for example, if 1 is off, on or 2 is off, or 3 or 4, for the rest of the combination, we are providing highest possible speed. That is this actually. So that is why it is providing the 100 kilowatt. Now it is 50%. Now put it on, put it off, and then put it on. Yeah, it is providing the 75%.
Yeah.
So again, I mean, same thing, the same principle PWM can be used for the different purpose actually. Okay, so I think I better suggest you to first of all to come up with that. I mean that solution. Okay, I mean that rotary encoder based a display solution. Okay. I think that one will have both the rotary encoder. You display at the same time. You have analog right. So one application, one program, one task that will enhance the skills in 3 sections. I think you come up with that. So you have another plenty of section. We can have, let's say, I have done some PIR based visitor counter, 2 types of this. One is the LCD based, one is a 7-segment based, and we have a lot more other interesting features to come up, and we can have that session also. Okay. So one this I think, and if you have time, then you can let's say you can keep playing with that RGB LEDs also. For example, if you want to provide any other colors also, and you can make it. I provide you. I mean, I suggest you to come up with a hardware solution also. I mean, for this RGB to see whether the colors are actually being reflected or not. Because Tinkercad it's okay, but my RGB LEDs are not so good actually. I've tasted them.
I have a couple of RGB. I'll try.
Okay, I'll try to see whether the colors are actually good, because my one is not getting. RGB fine,
Yeah.
YOLO is fine, but not all the colors are being reflected properly. I don't know why. What's the problem? But let me cross check.
Maybe there might be some voltage problem.
Voltage problem. But actually, once I put the 255 and I set the 5 voltage in my DC power supply, it's not getting the proper green one actually. The green one.
That's what might be the voltage problem, and other than that, it cannot be.
Definitely. Yeah, obviously. Okay, fine. So I think it's better to end up here, right? Today.
Yeah, we'll end up.
Okay, sure. So we'll come to the maybe Sunday or Monday. I think we take a 2 days break, right? Come up with a solution. Anything I'll share with. I'll attach all such.
Definitely, I have to go through all these codes right from long.